Hello everybody and welcome to the 16th webinar in the RUS series. My name is Georgia Karadimou and this webinar's topic is Earthquake Deformation with Sentinel-1. We will employ RUS to learn how to process Sentinel-1 SLC data to obtain the deformation caused by earthquakes using INSAR technique, and afterwards we will combine these results with geological data. I will show you how to access the RUS service and how to download and process the free data acquired by the Copernicus satellite. But also be aware that this webinar is being recorded and you will be able to repeat the exercise by yourself later, since this recording will be available both in our YouTube channel and our training website. I will give you more information on that in a while. The webinar will last around 1.5 hours, and as a start I will briefly introduce the study area. I will give you some information about Sentinel-1 satellite and INSAR technique. Then I will provide you some details about the RUS service, and finally we will proceed to the exercise that will be followed by the Q&A session. Please note that it is advisable to start sending us your questions immediately as soon as you have one and throughout the webinar, since we're here with my colleagues to answer to you as many questions as possible you have. This way we will not have too many questions accumulated for the Q&A session. Now let's have a look to our study area. During this webinar we will analyze the earthquake occurred on 4th of May in 2018 at the southeast of the Hawaii island after the eruption of Kilauea Volcano the day before. This earthquake was of magnitude 6.9 and produced around 5 meters of fault slip. It is the largest earthquake affecting this region after the one in 1975, where 2 people were killed and another 28 were injured. The aftershock events in the area continued until August 2018. Hawaii region is known as one of the around 60 hotspots that exist in the world, and its islands are formed due to the continuous flow of magma towards the surface. The seismic activity in this region is quite often, and in this slide you can see the earthquakes recorded at the area of study from 15 March 2018 to 15 August 2018 with magnitude 3.5 to 7. In blue we see the event of 4th May. So for this exercise we will be using C-band SAR data provided by the Sentinel-1B satellite. The Sentinel satellites are included in the space component of the Copernicus program of the European Commission and the European Space Agency. The Sentinel-1 mission is formed by a constellation of 2 twin satellites phased at 180 degrees to each other. It is an active sensor working on C-band. It includes a right-looking active phased array antenna providing fast scanning in elevation and azimuth, and it provides data with a short repeat cycles of 6 days. Here you can see the 4 different acquisition modes, of which we will use the interferometric wide swath and the 4 products of each mode, of which we will use SLC since it contains complex data of amplitude and phase and is necessary for interferometric processing. In the next slide you can see the 3 subswaths the interferometric wide swath consists of and the 9 bursts of each subswath. But let's talk a bit more about SAR interferometry. When we obtain 2 radar images over the same area that are of the same orbit and have the same geometry, we can create an interferogram which represents the deformation between 2 SAR acquisitions by calculating the phase difference of those 2 products. The interferometric phase consists of fringes, and one full color circle has values from -3.14 to +3.14. With interferometric processing, we can also obtain information about the coherence of 2 images. This means how well correlated is each pixel of the slave image to the corresponding to the master image pixel. The closer to 1 the value, the more coherent the image is. Finally, after having created our interferogram and applied all necessary steps, we can unwrap the phase. This means that we will convert the SAR units to absolute length units, and this will give us the displacement along the line of sight. Let's continue now to some information about RUS service. RUS stands for Research and User Support for Sentinel Core Products. It is an initiative funded by the European Commission and managed by ESA, with the objective to promote the uptake of Copernicus Sentinel data and support research and development activities. The service provides a free and open scalable platform in a powerful computing environment, hosting a suite of open source toolboxes pre-installed on virtual machines, which allow you to handle and process the data derived from the Sentinel satellites. What does that mean? Well, with a large amount of data produced by the Sentinel satellites, the challenge is not longer data availability, but rather storage and processing capacity. To solve that, RUS offers virtual machines so that you have the appropriate computing environment to handle the data. In addition to all that, RUS also provides a specialized user help desk to support your remote sensing activities with Sentinel data, and a dedicated training program. You can find all the information about the project and how to register on our websites, so I recommend you to check them after the webinar to get familiar with the service and see the VM specifications, list of software, etc. I will now quickly show them to you. This is the RUS training website. Here in the training you can find upcoming and past events. You can also access the e-learning portal. And here you can connect, you can log in and go to your virtual machine. You can find who we are, which are the computing environments we offer. And as I mentioned in the beginning, we also have a YouTube channel which you can find all the videos of our previous webinars, and you will also find this one in a couple of days. Regarding today's exercise, we will first select the part of the images that correspond to our study area. Then we will co-register them, and we will create an interferogram that will contain the information of both topography and deformation, and we will also derive the coherence band. This is the interferometric part. Next, we will proceed to the differential SAR interferometry, where we will remove the topography. Our interferogram will contain only the deformation along the line of sight, and we will create another output for phase unwrapping. For phase unwrapping, we will use snafu, and then we will import the result again to snap. This way, we will derive the displacement in absolute length values. Then we will convert the SAR coordinates to geographic coordinates and export the products for visualization in QGIS. There, we will combine the results with some relevant geological data. Let's log in to the RUS account and access the VM. So we go here to your RUS service, your dashboard. Here you can see that you can request a new user service if you don't have a VM. If you already have it, you can access it by clicking Access My Virtual Machine. You can get support from the support team or ask for a webinar kit. Let's access the virtual machine. So this is how it looks like. You can see all the software pre-installed. And now I will show you how to download the data we will need today. We open a browser, we navigate to the area of interest, which is Hawaii, and we set the parameters as sensing period 23rd of April 2018 to 5th of May 2018. We select mission Sentinel-1 as product type SLC, sensor mode IW, and relative orbit number 87 because the data have to be of the same geometry and be of the same orbit. We click search. We wait, and we will have two results. And once we have them, we just click on the download icon, and this is it. So now we can close this browser and move to Snap. So we launch Snap from the desktop, and we will load the two products we have downloaded. First, we will load the one of 23rd of April, and second, we will load the product of 5th of May. But let's navigate to the products for a while. If we expand it, we can see that it contains some folders. One of them contains metadata, which is important information about the data. But what we want to talk about is the bands folder, that if we expand it, we see that there are some bands. The I and the Q bands are the complex data, and thanks to that, we can derive the intensity band, which is a virtual band. It derives on fly by those complex bands. Here you can see that you have in this image 6 parts. 3 of them correspond to VH polarization and 3 of them to VV polarization. What we need is the VV polarization for our processing. I will just open here the intensity IW1 VV polarization band from the first product and also the same one from the second product, just to visualize them. And you can see that they are created on the right part. You can go to Window, Tile horizontally, and if you go to the Navigation tab, if you have those 2 buttons selected, you can synchronize the views. Here you can see that the geometry of the products is mirrored, and this is because snap visualization shows the pixels acquired first in the upper left corner. This is happening because our images were acquired during descending path, but we will fix that at the geocoding step in the end. We can also see that each subswath contains 9 bursts that have a black line between them. This will be removed at the deburst step. So now let's start our processing. Let's open a graph builder. Go to Tools, Graph Builder, and we will build a processing chain, and the aim of that is to save only the final step, not the intermediate products. This way we can save disk storage. Insert is a very computational heavy and RAM demanding processing, so we will try to save as much as possible. First, we will delete the write operator in order not to create confusion in the sequence. And for these pre-processing steps, we will just set the operators, but we will not set the parameters in the tabs below. As a first step, we need to split the product because the product has 9 bursts and we don't need all of them. So right click, go to Add, Radar, Sentinel-1 tops, tops are split, and we connect it to the read operator. Then we want to provide accurate satellite position and velocity information in both products. That is why we will add the apply orbit file operator by going to Radar, apply orbit file. And we connect it to the tops are split one. And at the end, we add again from input output the write operator to export the final product. Remember that we will not run it, we will just save it with the name preprocess graph to the folder we want. Once we save it, we close the graph builder and we open the batch processing tool. The batch processing tool helps us to apply the same steps to both images in one go. If you have more than 2 images, you can apply the same step for all of them. So what we need to do now is we click on Add Opened to add the 2 products we have in the Product Explorer window, and we click on the refresh icon. You see here the update of the products. Remember to deselect the Keep Source product name because we want the products to be stored. We load the graph we created before, and now you can see that 3 more new tabs appeared. So let's set the parameters. We go to the top SAR split and we select from subswath the IW1. Why? Because if we zoom in, we can see that our area of interest belongs to this one. For what we want to study, we choose polarizations VV, and from all bursts we only need from 4 to 5, and this covers our area of interest. Then we move to apply orbit file, and we select do not fail if new orbit file is not found. And finally, at the right one, we see that the suffix orb is added. We keep the default name, we set the directory of the output, and we run it. I'm not going to run it now because I have pre-processed the data. I will show you the results. So now I'm loading the results with the updated orbits and the products that are already split. Okay. So here, if you open the product, you can see that the bands folder now contains only 3 bands. And here you see the 2 bursts, and still this black line in between. So let's continue our processing. Now we will move to the interferometric part. We will create again a graph builder. We will delete the write operator, but in order to make it a bit faster, I will not create one by one the operators. I will load the graph that I have already created. So here you can see some operators. Let's go one by one to see what are the inputs. We have 2 read operators because we want to read the 2 products that have updated orbits. So in the first read tab, we have the first product of 23rd of April. In the second read tab, we have the product of 5th of May. What we want to do now is to co-register the 2 images. So we need to add the back geocoding operator. Remember that to add the operators, you right-click, you go to Add, Radar, and then you navigate to the appropriate one to add the operator you need. In the back geocoding tab, as digital elevation model, we choose SRTM 1 second auto download. We keep the DEM resampling method and the resampling time as by default, and remember to choose the output, deramp, and demode phase because this is a necessary step for the enhanced spectral diversity that is following back geocoding. So in this window, we keep all the default parameters, and this operator estimates a constant range offset for each burst using a small block of data in the center of the burst, and then it estimates a constant azimuth offset using an enhanced spectral diversity method. Now it's time to create the interferogram of the 2 images. And this interferogram will contain information for both topography and deformation. We do not change any parameters apart from the coherence range window size that we set it to 18. If you see, as soon as you change this value, the coherence azimuth window size changes automatically to 5. The next step is to put the topstar deburst operator, which will be responsible to remove, as I said before, the black part between the 2 bursts. Why do we have this? Because there is overlapping information in every burst with its neighboring ones, both in range and azimuth direction, in order to provide contiguous coverage of the ground. Until now, each burst has been processed as a separate SLC image, but now we will merge them in azimuth direction. This way we will also preserve the phase information. So we go here, we see that we only have polarization VV, and this is what we wanted. And finally we go to Write tab to write the output. We can give this name to the product. We don't need to keep the long one created by default, but we keep all the suffixes. So we name it S1B, IW1, the date of the product, orb, stack, IFC, and dep. Again, you choose the directory output. Before you run it, remember to save it and save it as process graph 1. And then you run it. Now I will show you the result of that. So I open it, and in the bands, you see that apart from the intensity, which is a virtual band, we also have the phase and the coherence band. If you double click on phase and on coherence, you can see these results. The values of coherence range from 0 to 1. Next step is to create another graph builder. So again, we go to Tools, Graph Builder, and we will load again the graph we have created. So this is the second graph. So first of all, what we need to do is to remove the phase, the topographic phase, from the dispersed interferogram. So as read, we put the output of the previous graph. In the top of phase removal, we select again as digital elevation model SRTM 1 second, and we can optionally choose one of the three or as many as we want of these options, and we select output topographic phase band. Then we want to apply the multi-look operator because we want to reduce the spectral noise that originally appears to the SAR images. This way we will obtain square pixels. You can see that here the only thing we will change is number of range looks. We set them to 6, and the number of azimuth looks changes to 2. This way we will have square pixel of around 27 meters, which is what we want. Then we continue to the Goldstein phase filtering operator, and this one reduces the phase noise. It is a necessary step since it will enhance the phase unwrapping accuracy for the upcoming step. What we do here is we enhance it a bit by choosing as FFT size 128. Then we want to export this product to save it as it is, and then export another one for the unwrapping analysis. So first we add the write operator to save it, and you see that it is adding the DINSAR ML FLD suffixes, and we keep the name as it is. Then we add the SNAFU export one, and we need to set the target folder. We need to create a folder to save the information. So we go to the appropriate folder and we write as file name SNAFU, and we select it. When we do it, you see that here the SNAFU folder appears in the target folder path. We choose as initial method the MCF. In number of tile rows and tile columns we set 1, and in row overlap and column overlap we set them to 0 because we don't want to have any potential problems. Again, we save the graph, we name it process graph 2, and then we run it. And now I will show you the results of those two operators that we exported the products. The first one is this one. So if I open the bands folder, I see the phase. We now see that it is multi-looked, and here you can see the units of the phase, the minimum and the maximum, how it varies, and you can also see the coherence. This is the phase that is multi-looked. Okay, let's continue now. The other output about SNAFU, if we go to the target folder that we created, we see the SNAFU folder that if we open it, it contains this information. What we need to do now is to unwrap the phase. This is the only part that is not being processed straight into Snap. So now we need to open a command line, right click in this folder, and we open terminal here. We see that the path is already here. And now we need to open the SNAFU conf file that was created from this output. Remember to go to the log file line. You can go to view line numbers to see the line numbers. Go in front of log file and add a comment and leave a space and save it. Then copy from line 7 the name as it is and paste it in the terminal and press enter to run it. So the result of this processing will be this one with the suffix HDR. Now that we have created this product, we want to import again these results in Snap. So we go back to Snap, we go to Radar, Interferometric, Unwrapping, SNAFU import, and we see some tabs. In the first read phase tab, we keep this product that was created before from the right operator from the previous graph. In the second one, we put the unwrapped phase, we click here, we navigate to the folder, and we choose this product that was created from SNAFU. In the SNAFU import tab, we select do not save wrapped interferogram in the target product. And finally, in write, we add at the end of the name the unwrapped suffix, and we run it. So the result of that is this one, the unwrapped one. And here in the bands, you can see the phase as it is unwrapped. Now it is time to convert the interferometric phase to displacement to get the absolute units. For this reason, we go to Radar, Interferometric, Products, and Phase to Displacement. In the I/O Parameters tab, we select the product with the unwrapped suffix. You can see that the displacement one is added, and in the processing parameters there is nothing to set, so we just run it. The final product of this step is this one, but we have a displacement map. We can import a color palette that we have created in advance in the auxiliary data folder in order to view better the results. The minimum is minus 0.34, the maximum 0.32. The red color indicates that the area was moved away from the satellite, and the blue one that the area moved closer to the satellite. This we will interpret it later when we will visualize it in Qgis. Now it is time to apply the geocoding. We will use the terrain correction in the products, in both products, because we want to convert the radar coordinates to geographic coordinates. For this reason, we go to Radar, Geometric, Terrain Correction, Range Doppler Terrain Correction, and first we apply it for the one product. You can see that the TC suffix is added, and in the processing parameters, as source bands, we can choose whatever we want. In this case, we choose intensity, phase, top of phase, and coherence. As digital elevation model, we select again SRTM 1 second auto download. We leave the rest parameters by default. And we make sure that the mask out areas without elevation is selected. And we click run. We repeat the same for the other product that contains the displacement, and we set again the parameters as we said before. So let's see now the terrain corrected products. This is the one, and this is the other one. Okay. So you can see that the phase now is terrain corrected, as well as the coherence band. Let's show them in parallel. And although we changed the option To remove the data that correspond to C, we can see here the pixels that still exist. This is happening because we used the SRTM 1 second DEM that has 30-meter resolution. If we were using the SRTM 3 seconds DEM, these pixels will have been removed. But now we will just apply one extra step. We will go to raster, masks, land sea mask. We will select those two terrain corrected products. We will go to the processing parameters and we will choose mask out the sea. It uses SRTM 3 seconds and we run it. And we apply also the same for the second terrain corrected product. Now if I load those two results and I compare them, you can see if we go to tile horizontally, you can see that now we don't have any more the pixels that correspond to C. The same is happening also with the displacement product. Again, here you can load sometimes you need to zoom in and out. Okay. Now it's time to export these products to visualize them in QGIS. You select the product you want to export. What we want to export right now is the two terrain corrected products, both of them. So let's go to the first one. We select it. We go to File, Export, GeoTIFF. We choose the folder we want to save it. We go to Subset. We want to go to Band Subset. And here you see the displacement, because this is the terrain corrected, the product that has terrain correction about displacement. We click OK and we name it as displacement TIFF. Now we will do the same for the other product. And we subset it. And for example, right now I will subset only the coherence band. I click OK and I put as a name coherence. And I export the products. So now let's move to QGIS. I have already created the session that I have loaded the coherence and the displacement. And also I have added the faults of Hawaii and the geology of Hawaii. Here, if I add the coherence to be visualized, I went to properties and I have it to transparency 40%. You can change that. And also you can go to geology properties. Here I categorize them by age range. I classified it and this is the result, how it looks like. You can classify the area as you want. And here you can see that although the SATE file is quite old, from 2007, it corresponds quite well to the geology of the area. Now we deselect coherence Hawaii and we select displacement Hawaii. This is how it looks like. Again, we can change the transparency and see how it looks like. Here you can also add this color palette by going to Style, load the pre-saved displacement style, and this is how it looks like. Now that we have all the results, you can also export them as Google Earth files. We can go back to Snap. We can select the product we want. We go to File, Export, Other, View as Google Earth KMZ, and we export it. And now I will show you how to interact your virtual machine with your laptop. If you press Ctrl, Alt and Shift, this window is opening. If you click here and you navigate to the folder you want, you can just double click on what you want to download, for example the coherence TIFF, and once you double click it starts automatically to be downloaded. You can also navigate to the appropriate folder you want to upload something, go to Upload Files, and then go immediately to the window of your PC and load anything you want. Now I will just shortly show you in Google Earth how the results look like. So this is our study area, these are the fringes, this is the deformation, and you can see that also we have the faults. We can deselect the face and we can load the coherence, and you can see how well it looks. Also you can change here the transparency as well to view the layer of Google Earth. Now that we have finished with this part, I have something last to tell you. With the new Sentinel satellites, the challenge is satellite remote sensing. In satellite remote sensing is no longer data availability, but rather how to store and process all the information. In addition to that, it is necessary to explain how the data can be used and support users in their applications. The RUS service is here to solve those problems by providing virtual machines to store and process the data, and by offering a dedicated help desk supported by a team of remote sensing experts to help you in your project with Sentinel data. So before moving to the Q&A session, let me tell you again that you can repeat this exercise by your own if you want, to practice or adapt the methodology to your own application. For that, go to ruscopernicus.eu, register in RUS and apply for a virtual machine. During that process, you just need to specify the training code HAZA05. You will receive the training kit that contains the PDF of the step-by-step guide and the auxiliary data. So this was all from my side. Thank you very much for attending, and see you in the future webinars that we will launch. Ciao!